So welcome everybody to today's webinar. It's going to take about an hour, and as we've said, if you have any queries during the presentation, put them in the chat. If you have any queries or any questions, again, put them in the chat. If we don't answer them today, we'll answer them at another time. And if you don't have a problem with that, just email Kirsty and we can answer any questions. So what we're going to do for an hour today is to outline how mechanical power transmission has been used by man throughout history to create and develop the machines that have become essential to our civilization and way of life. And the critical role gears play in this technology is explained in how for more than 2,000 years, gear engineers have embraced all aspects of mechanical engineering. And the challenge continues, providing exciting opportunities for engineers involved with gears and gearboxes. I will show you that we've been using gears for 4,000 years, and they're still as important now as they ever have been. And hidden within is a secret joy, a joy associated with gears that will be revealed during the course. But first, just let me give myself a little bit of an introduction. It's over 50 years ago that I joined the gear industry, and I got my job with the David Brown Corporation as a stress analyst. And at that time, David Brown made tractors. David Brown owned a shipyard that made ships. It also made Aston Martin sports cars. But I joined the headquarters where they made gears. And I thought, you know, in 2 years, I'll know everything there is to know about gears. And then I'll move on to something more exciting, tractors, sports cars and warships, battleships. But no, here I am, 50 years later, still learning something new about gears every week and still getting a great deal of pleasure out of gears. And that's what I'm going to do for the next hour, just go through mechanical power transmission and the joy I've got out of gears, and hope we can spread that joy a little. So just let me go through the agenda. What we're going to do today is to go through the history of mechanical power transmission, just show you why it always has been and always will be critical to our way of life, how the development of practical engines and the first industrial revolution increased the demand for mechanical power transmission, and how further engines allowed mechanization to develop and increase. And then we'll talk about the joy of gears and then finish off with industry 3 and 4. I know these are new terms, but we're going to talk about the way the Internet of Things and how gear engineers are still got an important role to play and will continue to have this important role to play as we go further forward. So first of all, why is mechanical power transmission so important? So this is just definitions. Although I'm sorry, I'm jumping about a bit because I seem to be losing control now and again. But very simply, any machine that does work and uses energy and power will require mechanical power transmission. So every machine you will ever use will have some sort of mechanical power transmission. And engineers is someone who designs, makes or works with machines or machinery. So that's really good news, because it says if you're an engineer, as long as man wants to use their machines, people are going to have a need for you. And so we're going to explore that a bit. So I said, if we go back over 4,000 years, now this is a model of a south pointing chariot. And this was used by people in China over 2600 BC, that's over 4,000 years ago. So you see that arrangement of very crude gears and cogs and actually a differential. Somebody invented that over 4,000 years ago. People were using gears so long ago. If we move back a little further forward, this is only 2,000 years old, but this is a device to track the planets going around the solar system. So we could use it for navigation, and so we could look at the stars. And this is 2,000 years ago. People were using gears. And that's the point. We've used them. All these machines and devices have been using gears and mechanical power transmission. But let's talk about power transmission, not so much devices to do calculations, but let's have a look at some machines powered by people. So here we have, and we're going to call it an Egyptian shadoof. Now, we're only calling it an Egyptian one because they kept proper records. But what you can see here is the prime mover. And what I mean by that, that is providing the power for this machine. We've got here just somebody irrigating, taking water from the Nile and irrigating his crops. Let's think about that. The prime mover is a man and the driven machine is this water lifting bucket. So the mechanical power transmission here is just that lever which gives the mechanical advantage and the ability to store engine. So what the man does, he pulls down on the rope, puts the water in the Nile, and as he does that, he's storing energy in that rock which is lifted. And then when the water bucket's full, the stored energy and him pulling up helps him to bring up much more water than he would have been able to before and transfer it across. So that is a mechanical power transmission. Very crude, very simple. The motion is discontinuous. And what I mean by that, it's up and down, up and down. So what I'd like to move on to now is another machine. Now then, what we've got here is a rotating machine. So it's a Persian water wheel taken from drawings from long ago. And I want to explain two things. We have a prime mover and a driven machine. In this situation, the prime mover is the camel and the driven machine is water lifting buckets. But unlike the one before where it was discontinuous motion going up and down, this is continuous. So both of these machines, both of these are running at their ideal conditions. Now the camel probably doesn't appreciate this, but he's walking around on a horizontal plane, and the man who put this together has designed this that the camel can walk around at a steady pace, so he can spend all day without getting too tired. He will get tired, but he won't be overtired, going round and round in circles, supplying the power. Now what we've got there is some crude gears, pegs, whatever it has, and that is changing not only the speed of rotation, but the direction. And it's doing that so that driven machine, the water lifting buckets, can go to continuously and at the right speed, not too fast so the water spills out or they don't get filled when they go down, but at ideal conditions. And that is the point. What we've got there is gears, mechanical power transmission, are allowing the prime mover and the driven machine to run at the ideal conditions. Again, the camel really doesn't appreciate that, but that's what's happening. And so as we move forward in history, as well as animals and people, we use gears and mechanical power transmission to harness the power of the wind. And it's the same message. And this one, this is a windmill. And what this is doing, those blades are going around. The prime mover is the wind, and the blades are catching the power from the wind and going round and round. And within there, there's a set of gears changing the power, changing the axis of power, and letting the grinding wheels go at the right conditions. A common message is coming out. We're finding prime movers, which may have been men, camels, in this case the wind. We're harnessing that power by mechanical power transmission. And of course, we use machines powered by water. In this case, we're talking about water wheels. And if you look at the pictures on the right, you can see we can have the water coming in at the bottom of the water wheel, halfway up, halfway down. And we have a system of levers, pulleys, gears, whatever it is to harness that power. So again, we keep seeing it's the same message where we're harnessing the power of people, animals, and renewable sources. Yes, we're going back to that, but we're harnessing the power of wind and water through mechanical power transmission. But as we go through history, man really wasn't that satisfied. So he wanted to find engines which he could control. He didn't have to wait for the wind to blow. He didn't have to wait for the water to run. he wanted a machine where he could power. And this is a very, very early engine. And an engine is just a machine that is used to convert some sort of energy into mechanical energy. And that can be used to perform useful work. Now, in this case, this is Hero's engine. It wasn't ever practically used to drive machines. But if you look at this diagram, what we've got at the top is a big sphere, and it's fed by two pipes, LMC and GFD, and those are connected to a chamber of water. And beneath that chamber of water, we light a fire. And all that fire is doing is converting that water to steam. The steam goes up those pipes into that sphere, and you can see the two outlet nozzles allow that to spin around. And so, if you like, it's a very, very early steam turbine. And that was developed 200 years BC, over 2,000 years ago. So somebody's saying, well, I'm not going to rely on the wind and the rain. I'm going to be in control, and I'm going to use some sort of natural resources, whether it's wood to light the fire or whatever it is. I'm going to start harnessing energy and be in control. Now, that wasn't practical, and so we had to wait quite a while. And then we got the first practical industrial engine, and that actually required a new word. So what I've got here is one of James Watt's steam engines, and you can see there we are using steam. I'm not going to go into the details of it, but what we have there is pistons. And so as you create the steam, you put it into a piston, it goes to and fro as it expands, and you get those pulleys to go up and down and start doing useful work. And those early ones were used actually for mines, where people were mining underground to get coal and tin, to go up and down to drain the mines from water so we could dig deeper to get the raw materials we wanted to use. And it's interesting. Until that time, we didn't have the word horsepower, but James Watt invented the word horsepower, and he needed it to prove, well, I've got the steam engine. I want to show people how powerful it is. And so he invented the term horsepower to say, look, this is a 50 horsepower steam engine. It's got the power of 50 horses. And there's a certain irony in that, because we sort of stopped using the word horsepower now. We use watt. And so it's certainly ironic that the man who invented the word horsepower, his word isn't used anymore. So we've started using a new word, watts and kilowatts, named after him. But let's think hard about this. This gave us the first industrial revolution. We need to think hard about this, because what it had there, this is a Cornish pumping engine you can see here. And we don't now just say the industrial revolution. We say it was the first industrial revolution. And let me explain that. You had a single machine for many users. And as I explained, this is the Cornish pumping engine. At that time, in Cornwall, part of the United Kingdom, they were mining for tin, a very valuable resource. Tin was very valuable. You used it, it didn't rust, you used it for lots of things. And the mines in Cornwall were getting deeper and deeper, and they were going under the sea to get the tin. But the problem was, as you got deeper and got under the sea, there was a lot of water in the mines, and you couldn't go much further until you could drain it. And so this big one machine was there to drain the mines of water so you could carry on mining and getting these raw materials. So one big machine allowing many miners to work there. And that was the first industrial revolution. One big machine doing this work. And you can see on all these pictures, we've got mechanical power transmission. It is a common theme. We also had the mechanization of factories. So this is a cotton manufacturer in Great Britain. And in this one, it may be difficult to see, but it's an old sketch of it. We'd have one big steam engine driving shafts going around. And you look at the ceiling above there, you have these shafts going along, and you can see pulleys and belts. And each of those pulleys and belts were connected to those spinning and weaving machines in this cotton factory. This was long before the days of health and safety legislation, and you had these belts spinning around, connecting all these machines. So we could start having factories, mechanization of factories, producing cotton wool and all these other things. So one big machine with many users. In addition to that, yes, we had factories, we had coal mines, we had mines producing all this output, and you had these cotton factories producing cloth and wool, whatever it was. So you had all these products and you had to do something with it. You had to distribute it. And so we developed steam engines and transport systems in order to get the coal we'd mined, the cloth we'd manufactured, get it out to ports, get it out to ships and sell it all around the country. And this was happening all over the world. Once we'd started getting these machines, that happened. And again, each of these machines has got mechanical power transmission in there, whether it's belts, pulleys, or even gears in there, it's used all the time. So that's Industry 1, the first industrial revolution. But then development was going on all the time. So in addition to the big steam engines, and yes, you could have small steam engines. If we look at this diagram, you can see we've got a very early electric motor, and then we've got a picture of a internal combustion engine. And then the bottom right, we've actually got a picture of the first steam turbine that was practically used. Remember that one Hero's engines from 2000 years ago? Well, that was in the first ship to have a steam turbine, and that went at a speed nobody could believe, the speed of that ship. But what I want to get you to think there, because these machines, these prime movers are now getting smaller and smaller, you could have many machines for many users. You weren't relying on one big machine with lots of users, like we had at the coal mines or in the cotton factories. You had many machines for many users. And this pretty much heralded Industry 2, mechanization. And we take these things for granted. And I just want to show you a picture there of, if you like, Henry Ford and the Model T car. And that was 1908. And yes, I know Henry Ford didn't invent the first practical car. He didn't invent the first internal combustion engine, but he did something, two things incredibly important. He invented mass production. So he said, I've got this car and I'm going to start mass producing them. And the mass production of cars did two things. First of all, it reduced the cost of these cars. It reduced the cost so they were more affordable. You weren't just making one, you were making hundreds at a time. And it did two things. It reduced the cost of production. It made products more affordable. And the other thing, which isn't usually recognized, all of the workers in the factory got a step change in their wages. They got more money. And that meant they were in a better position to buy these products. And it wasn't just cars. Remember the cotton factory. Once we started having mass production, then the cost of products got cheaper, and the people employed with them still didn't get massive wages, but they got regular wages, but they were getting wages which meant they can afford them. And this is the thing we take for granted. At the beginning of the 20th century, who would have believed that within 20 or 30 years, everybody had access to their own means of transport? Everybody taking for granted. If you go back 200 years and told people you'd have your own vehicle, you could travel around the country, go wherever you wanted, they wouldn't believe you. But that's what happened. And again, I haven't forgotten about mechanical power transmission or gears, but in that car, then we know there's lots of gears. We know there's mechanical power transmission. But equally important, have a look at the factory. There's gears, there's mechanical power transmission. And it keeps emphasizing not only did the products demand mechanical power transmission, the means of production did. So let's go through this again. Just let me think about it. What I said is all of these cases, mechanical power transmission allows the prime mover and the driven machine to run at their ideal conditions, whether it's a camel going round in circles or water buckets going up and down, or whether it's an internal combustion engine driving wheels, it lets them run at the right conditions. It does that. And now I'm going to bring you an equation, the key to power transmission. And I'm sure you're all engineers and you know this already, but power equals torque times speed. And look, that name's come up again. So a coherent set of units, watts equals Newton meters times radians per second. Power equals torque times speed. That equation, and what that says for a certain amount of power, whether it's coming from a camel, whether it's coming from a man, or whether it's coming from an internal combustion engine, if you reduce the speed, you increase the torque. And you know that if you've ridden a bike or driven a car and changed gear, if you need more torque, if you have to go up a steep hill, yes, you have to change a gear, whether you're riding a bike or in a car, so you can have more torque, but you have to go slower. And the opposite is true. If you increase the speed, you reduce the torque. Now, everybody should know that. Everybody should know that you do that. Basic mechanical power transmission, but don't ever forget that. Now, there isn't there another hidden advantage, and people don't always appreciate that. If you're engineers, you understand torque is the twisting force, and all the rotational stresses vary with torque. So just think about what I've just said. If I double the speed in a power transmission system, so if I want, say, the prime mover, I want it to go a bit faster, I want it to go twice as fast, I'm halving the torque it has to produce. And what people don't always fully appreciate, that means I'm halving the stresses. And so if I halve the stresses, I can reduce the size of the components. I could reduce the cost of the components. I can make them smaller and cheaper. And that's another thing that we can do with mechanical power transmission. Let me change the speed. Yeah, there's certain things come. If you make things go too fast, you've got to think about centrifugal forces, bearings, and all those things there. But basically, the faster it goes, the lighter, smaller, and cheaper you can make it. And you appreciate that, you can make things a lot more interesting. So it's doing all of these things. But why gears? Well, let's have a look at this. And this is, again, for those of you who are members of the BGA, this is taken from one of our teaching packs. And what I'm doing here is just comparing different sorts of mechanical power transmission. Now, I'm talking spur and helical gears, bevel gears, worm gears, but also remember belts, V-belts, tooth belts, roller chains, Morse chains, and friction drives. All of those mechanical power can do those things. Yes, they can change the speed. But just let's have a look down the column. First of all, those are the normal ratios we can get from these devices, and the ratio is how much you can reduce or indeed increase the speed. And then the next column down is the maximum power per mesh, whether it's in kilowatts. So for spur and helical gears, we can actually per mesh transmit 30,000 kilowatts. 30,000, so that's 30 megawatts, that's 30,000, if you like, horses, massive amounts of power you can get through gears. Bevel gears, we can transmit almost 5,000, worm gears, and we can run those at speeds up to 100,000. But just go down the column. Yes, belts, you can transmit a lot of power, but it reduces as you go down. Nothing really can compare with spur and helical gears for power, maximum power. And actually for speed, maximum speed, 100,000 revolutions per minute for spur and helical gears. Bevel gears can go pretty quick as well. Actually, the fastest things about in that list there are flat belts. And these are flat belts which can go at phenomenally high speeds. Not as much power as gears, but they can go faster. But all those there. But generally, if you look at that list, gears tend to come out near the top when it comes to power density and speed. But also look at the efficiencies. Incredibly efficient. And in that one there, worm gears don't look so efficient. But with worm gears, you can get ratios up to 100:1, almost off the shelf. When you have those high ratios, they may not be the most efficient. Well, these are all pretty efficient devices. But gears have a very other significant advantage. I say it's flexibility, but let's have a look at the flexibility, because what I'm going to talk about there is, look at this picture. Look at those pictures of gears, and we can see that unlike belts and pulleys and chains, just a minute, I seem to have lost control. Let me just grab it back. Unlike belts and chains and belts, with gears, we can change the axis of power through 90 degrees, or we don't even have the center. So at the top left there, we've got right angle gears at 90 degrees. In the center, we have hypoid gears. So we've changed the axis of power through 90 degrees, but lowered the pinion. Bottom right is a spiral bevel gear. Bottom left is a worm gear. Top right is very interesting. That's a crossed axis gears. So with the crossed axis gears, we can actually, if you're very clever with the design, you don't have to have that angle at 90 degrees. You can have it any angle in between. They're quite complicated to design, but you can do it. So mechanical power transmission helps you, or lets you, run your prime mover and driven machine at their ideal conditions and at the ideal speed, and also make them lighter and cheaper. But if you use gears, you can put the prime movers and driven machines exactly where you want them. They don't have to be parallel. You can put them at 90 degrees or indeed any other angle you want to. So that's why gears tend to be becoming so useful and important. And remember, we've got all these devices with small prime movers, electric motors, internal combustion engines, and we can make this mechanical power transmission to develop lots of interesting machines. And I just want to explore that a bit. Let's just go back a bit. Let's have a look at horsepower. And remember, James Watt invented horsepower, so he could show how powerful his steam engines were. So obviously, looking at this machine there, which is just a farmer with a horse, and he's just going around turning over I think it's a grass he's got to make into hay, but that is clearly, no question, a 1 horsepower machine. Now, if you have a big farm, say in the USA, going back a little while, you may need a bigger machine. So let's have a look at a 30 horsepower machine. Now, I was quite staggered when I saw this. I actually didn't believe it, but this was the truth of it. A combine harvester going back, where you have about 30 horses. Now, I actually say I'm not convinced all those 30 horses are pulling their own weight, but if you want to harvest all of that wheat or all that wheat that's there, you need that sort of power to do it. And so imagine you're a farmer, you've got to feed, you've got to look after all those horses, you've got to make them all pull their own weight, you've got to put shoes on them. It's quite awkward. But let's just think what happens when you've got an internal combustion engine and a machine. And there you have a 30 horsepower tractor. And because I used to work at David Brown, that's a David Brown tractor. And by the way, it's quite an old David Brown tractor, but it's 30 horses. And the truth is, that can do all of the work of those 30 horses at the top right there. And all I've got there is an internal combustion engine. Within that quite old tractor, there's a 30 horsepower internal combustion engine. And then what we have is a multi-ratio gearbox to allow the engine and the wheels to run at the right speeds if the man wants to go faster or slower, so we can change gear, change speed. But in addition to that, he's got a bevel gear to put the axis of power through 90 degrees to drive those 2 big wheels at the back. He's also got a differential gearbox in there to allow the tractor to go around corners and have the right amount, let the wheels go at different speed when it goes around a corner and have the right amount of torque going there. But also, very cleverly in there, you can put in power takeoffs to drive lots of other machines. So just think about that massive step you get there, that internal combustion engine, gears and mechanical power transmission gives you. You can do all of that work with one man on a tractor. And by the way, it probably uses less energy and produces less pollution than 30 horses because you can control it. Now, whether you're using renewable sources or not is a different question for another day. But that, as I say, that's an old tractor. Let's have a look at a 300 horsepower tractor. And that isn't a lie. What you've got there is a tractor that can do the work of 300 horses. And by the way, that's a John Deere tractor. I think people are developing much larger tractors. Now, I'm not going to get involved in global warming and all those other things, but I'll give you a thought before I move on. And the thought is this. At the beginning of the 20th century, the whole world had about 1 billion people. And at the end of the 20th century, it had about 5 billion people. And we were farming less land, or certainly no more, because 5 billion people take up a lot of land. So in order to feed all those people, you demanded to have large tractors and machines. Now, even though I say the tractors are probably more efficient use of energy than the horses, because there's less wastage and what have you, you're still using a lot of people, but equally, you've got to feed people. So that's a thought. We're not going to go there today, but it's just showing you how engineers are required to do it and how we take for granted all those things which are happening at the moment, all those machines we have. Everybody listening to this probably has access to their own modes of transport, whether it's a motorbike, whether it's a car, whether they go on a bus. We take it for granted and all those things that they get. And I just want to know a little bit forward into that. So let's look at personal transport. Again, I'll stop going on about David Brown in a minute, but that's an Aston Martin car, and that's an Aston Martin sports car, quite an old one these days, but more than 300 horsepower in that. And that's incredible. You think 300 horsepower, and that's wonderful. You know, how much power can I have just to drive to shops and whatever it is I do? But that engine isn't perfect. Let me re-emphasize the point. It only develops that much power at 9,000 RPM. And if I wanted to drive those back wheels at 9,000 RPM, that Aston Martin would have to go 400 miles an hour. And even an Aston Martin doesn't do that. So you need to modify that power. Yes, we can position it at the front of the car, and we can use gears to change the speed. We can use a differential gearbox and a bevel gear to drive two wheels at different speeds and go around corners. So we use all those things there. And we use gear and gearboxes to do all those things we mentioned, allowing the prime mover to run its ideal conditions and indeed the car. And if we go over to the right, we actually see an electric car. And those of you who had a chance to drive an electric car, you think, well, actually, don't need a gearbox, don't need to change gear. And that's because of the torque characteristics of the car. We'll come on to that in a little while. But whilst you may not be changing gears, the truth is that all electric cars have a few gears and gearboxes in there. Yes, they need a right angle drive, and we need a differential to drive those wheels to go around corners. Also, believe it or not, to get that electric motor to run its ideal conditions, you'll probably have at least one ratio in there. Remember what we said, make the electric motor move faster, the torques reduce, it gets lighter, cheaper and more convenient to make. So there'll be a fixed ratio gearbox in there. You won't have the 6 ratio gearbox you often have in cars. You don't need that because of the torque, but you still need gears in there to do it. So all these things are happening. We're using mechanical power transmission and gears as we use machines, and we take these for granted. And so let me quickly skip through a few pictures. When you transport goods, where you've got big container ships, when you've got cranes, all of these things there, we'll see gears, gearboxes, mechanical power transmission, water treatment and management. If you've got that's a Thames barrier if you want to make sure things don't flood, or you want to treat water, sewage management. You've got gears and gearboxes doing it. If you're making steel, if you've got steel mills, everywhere you go, machines do it. Even when we're getting power. So if now it isn't the wind turbines, the windmills we looked at before, these are wind turbines, and what you've got there is epicyclic gearboxes in there. Talk about these in a little minute, because that's a very interesting application. So if we're going renewable energy, yes, wind, over 90% of wind turbines have gearboxes in there. You can actually have wind turbines where you get the alternator to run at exactly the same speed as the rotors. These tend to be very heavy tower top masses, but I think it's no more than 10% of wind turbines don't have a gearbox. Look at solar power. That's a solar power station. That's a schematic of a 100 megawatt solar power station. And around there, you have something like 6,000 mirrors. And each of those mirrors in this particular instance has two drives. One is a tilting device to make sure the mirror tilts. Another is an azimuth drive. An azimuth drive, so the mirrors can follow the sun throughout the day to collect power to do it. Now, in that application, each of those 6,000 mirrors had two sets of gears in there to tilt the mirror and rotate it to follow the sun. Not sure how much CO2 you used in making all those gears and gearboxes and how much you're going to save, but they're there to do. Even if we go to tidal power, you can see those schematic diagrams of a few different ways of tidal power, and these things are happening even as we speak. Each of those things are using gears and gearboxes. So now then, I've come to these things. What I've shown you there is throughout history, we've used mechanical power transmission, gears and gearboxes, and very briefly shown you that why that is the case. But there's a terrible, inescapable truth, and it's quite sad for somebody like me to say I spent my whole life being involved in gears, and the sad truth is nobody actually wants gears. They don't want them. They only have them because they need them. They need the gears and gearboxes and mechanical power transmission to allow the prime movers and driven machines to run at the ideal conditions. If by some magic prime movers could run at any speed or position, whatever you wanted, we wouldn't need gears, but at the moment we do. But there is another secret joy. Everybody needs it, and you can make machines that much better. And this is the revelation, which I will read out exactly as it says on there. And the revelation is this: to fully understand and appreciate gears, one of the simplest, oldest, and perhaps most elegant and precise of all mechanical components, it is necessary to grasp a vast range of engineering topics. And that is the joy of gears. They embrace so many technologies that there's always an opportunity to learn something new. And it's inevitable that once involved with gears, you will meet and enjoy working with many different and helpful engineering experts. And that is the joy. If you're going to get involved in gears, you've got to start learning a lot of engineering things. So now I'm going to spend a little time just going through these things a little. First of all, we need to understand the machines we use. We need to understand the power-speed relationships. Two diagrams there. The one on the right is a fan curve. You look at that fan curve. The fan curve there, the torque required by a fan there is, it goes up with a square of speed. So if you double the speed of a fan, you need 4 times as much torque. And on the left there is a vehicle. If you're going to drive a vehicle, you need to understand how much power it wants. And there's two components there. First of all, there's a rolling resistance, which is the green line. And secondly, there's the aerodynamic drag, which is the blue line. You put them both together and you get the red line. You need to understand what that driven machine wants. Equally, you need to know the prime mover, how much power is coming from that. So just have a look at these graphs here. What I'm plotting there is, again, torque against speed. Top left is an internal combustion engine. Top right is an electric motor. Bottom right is a steam turbine. So just have a look at that internal combustion engine, the top left one. You can see the torque, and you know this if you drive a car and change gear. The torque peaks and it tails away. So when you're driving an internal combustion engine car, yes, either you or the automatic transmission will be continuously changing gears up and down, so you're always at the peak of that torque or getting the right efficiency. Just go over to the right, where you can see the torque speed characteristics of an electric motor. Well, there's two curves on there. The bottom of that is a torque and the top one is the current required. But you look at the one at the bottom of those curves of the top right diagram, you can see at 0 speed you get an awful lot of torque, and as you go up to speed, you get to synchronous speed, you don't get any torque. Now, for years I've understood the mathematics of that, but until you actually sit and drive a car with an electric motor and electric drive, you're amazed how much torque you get at 0 speed. You put your foot on the accelerator, where else did that torque go? I don't have to change gear to move it. And it's quite staggering, but you do need to understand these things. You need to understand it. And again, there is the BGA, the British Gear Association, has a few teaching packs with details in here to help you out to do it. So if you're BGA members, we can dig these packs out to help you if you're doing that. So somebody has to put system designs together. So you do need to understand the system design. And what I'm going to show you here is a very simple way of looking at, I'm going to use an electric motor, and that's my diagram at the top left there, where I can see torque against speed. And I'm going to drive a fan. And so you go down, you can see that square curve underneath of the fan. And the diagram on the right shows me how I put those two things together. So what I've got there is the available torque from the electric motor, and then I've got the required torque from the fan. And you can see they only come together at the rated load. And at 0 speed, the fan isn't really demanding a lot of torque, but the blooming electric motors are supplying an awful lot. And so we have this overload capacity, which is great, because what it means, I've got more power than I need, and very quickly I'll get the system up to speed. And that's a great thing if you've got a light system with no inertia. It's like switching on a motor with a fan, it suddenly gets up to speed very quickly. But imagine in that system at a very large inertia, and all that torque was there trying to get these great big inertias, great big bodies up to speed. You might take minutes getting up to speed. All of the time you've got more available torque than you needed, and you may be overloading the system. So somebody with any system that's put together has to understand all these things and take responsibility. So if you did have a system which, say, had large inertias and you didn't want to spend too long getting up to speed, or if you were going to take time getting up to speed, you didn't really want to overload things, you could put a fluid coupling in there. You could put a torque limiting clutch in there. You could start getting a special motor which has a soft start motor. Those things have to be done, and somebody has to take responsibility. And it's just another of the technologies you need to embrace if you're looking at mechanical power transmission systems. So again, understand the loads in the system. There you've got there, the bottom right picture is actually showing you the load against time. And that's, say, at the start of a shift, 100 horsepower, 100 kilowatt machine, you start at 80 kilowatts, you go up to 120, then after lunch you go down to 60, then up to 125. You think you're in control, but you know, anybody who's measured loads, measured torques or powers, know that even in steady state, look at the steady state picture there, nothing's constant. And when you go from one stage to another, you get transient loads, things change. Nothing's ever constant. And so what you may think is a nice smooth load, in practice may be nothing like that. And just let me give you an example. This is understanding the loads in the system. This is a bit of a history lesson, and this is going back to when we had the first of the contemporary wind turbines, and it's going back to the 1980s. And I know it's probably a long time before many people here were born, but in the 1980s, we were first starting to get the new generation of wind turbines. And it's a very simple diagram. You look at the cut-in speed, you get up to speed and switch it on. And everybody thought it was going to be a very smooth system. But the truth is, in the 1980s, when we started developing large-scale wind turbines, the amount of failures was staggering. People just didn't understand what was going on in the system. Just let me go through this a bit. And so when we started having failures, people started deciding I better understand the system. And so what we did, look at the wind turbine. Yes, you've all been to college. You can all write differential equations. We can all do an analysis of the system. So what do? Well, look at this diagram. We start writing the equations of motion of lump masses. What we'll do is model the system. We'll make a whole series of lump masses, stiffnesses, and if there's damping in there, we'll put that there, and we'll write the equations of motion of each of those masses. So in the diagram there, the top left is the hub, the rotor going around, and we go all the way through the gearbox, through the pinions, the wheels, the couplings, across until the bottom right, we get to the alternator, and we have the rotor going around there, and then we connect it to the grid and writing all those equations of motion. And then if you're really clever, and this is where my maths capability met its limit, trying to remember Laplace transforms to solve differential equations. But luckily I was working with people who understood these things, and we could start doing all of these things to work out the loads in the system. But the thing you soon found out is the most rigid system, a rigid part of that system is the air gap between the rotor and the national grid. In this case, it was the USA Altamont Pass in California, where it's 60 Hertz. I'll come back to that in a minute. Remember that you've got this series of lump masses and stiffnesses, and I'm telling you now, the most rigid thing in there is an air gap between the rotor and the national grid. So in order to understand that, this is what we found. We actually not only did the analysis, we went out and measured the loads. And so what we do there is put strain gauges, top left there, you can see where we're putting strain gauges on there, and actually hired a crane to hang weights off the blades to do a mechanical calibration. So you know any Newton meters were hanging off the end of that rotor. But then look at the diagram on the right. We measured the loads in the system. The steady state, nothing like steady state. The load's going up and down all the time. It was supposed to be nominally 300 kilowatt machine, and we were typically measuring, even at steady state, loads up to 350, 400 kilowatts, 450, even 500 under steady state. And that's because the wind was gusting and the blades were trying to adjust their pitch to control the loads. And those early control systems weren't very good. And so if you did a Fourier analysis of that steady state, you'd be able to pick out blade passing frequency and stuff like that as well. But the biggest load in there, let's follow those graphs from the left. The bottom graph there is wind speed. But as you can see on the left, we're measuring torque and power. And somebody decided, okay, the wind's strong enough now, I'm going to switch it on. So you can see as the loads get larger and larger, because we've released the brakes and the blades are getting up to speed, it's generating electric power and the torque's going up. And then somebody decides, okay, we're running at the right speed now. We're generating power at 60 Hertz. Remember, this is in the USA where the national grid is 60 Hertz. It's 60 Hertz. We can plug it into the grid. And that is the point. Yes, you may have been at the right speed, 60 Hertz, but if you weren't exactly in phase with the national grid in the USA, the national grid would grab hold of you and get you in phase within milliseconds. Whatever load it took, it would put that rotor into phase with the grid. And that's why I say that air gap is the most rigid, unforgiving thing in there. because it'd take whatever power it needed to move all your inertia to speed. And the control system then weren't really good enough to do that. And sometimes blades were falling off machines because of the loads that were being transmitted. And we learned from it. And the truth is, when you learn from this, we start developing application factors. And those are critical when you're designing gears. Lots of the courses we run at the BGA cover this, where you have to understand for a particular application what sort of overloads you would expect. And so we have standards, international ISO standards, national standards will give you advice on application factors, industry standards, the wind turbine industry has its own standards, the petroleum industry has its own standards. You need to dig deep and understand what's going on in the system, because it's unlikely you're ever going to have the time or even the capability to do those differential equations. And clearly you can't measure loads till you've actually built the system. So as engineers, you're going to have to start relying on application factors and lessons from history. So yeah, we can calculate the loads, find them out, but then we have to manage them. And we won't go into too much detail here, but we start having to say, well, if you're going to design gears, everything you learned about stress analysis you need to understand, because those gear teeth are going to start suffering from contact stresses, bending stresses, and you've got to make sure there's no wear failures, because the surfaces will be sliding and rolling together, and you need to make sure there's no damage to the surfaces. Too much bending stress, you start getting cracks. So everything you learned about endurance limits, its strength of materials, Goodman diagrams, you will need to understand gear failure. And you need to understand about Hertzing stresses, contact stresses, things that you'll learn about, all those technologies you need to learn about and embrace. But it's not that difficult, because there's lots of standards about. In fact, the good news is there's lots of standards which cover all of the engineering topics and what have you. Perhaps the bad news is these are not straightforward. There's a lot of involvement in understanding these standards, but the methods are written down and you will have to dig deep into them. And another great advantage of the BGA, the British Gear Association, all members of the British Gear Association have access to the top 25 gear standards for 24/7. So if you want to look at the top ISO, BSI standards, you can go to them online. And so typically, if you had to buy all of those standards, it would cost you £6,500, but you can go online. You can't download them, but you can read them all online, take the equations and follow them. And you need to follow. You don't have any discretion these days. You have to follow international standards if you want approval for the things you're making and designing. A couple of things about that standard. Not enough time to go through any more with slightest detail, but I want you to take one principle of these standards. Look at bending stresses. Don't even going to spend much time going through that formula. But there's two concepts here. First of all, for the bending stress, remember you're going to try and bend that tooth off. The first thing you will calculate is a nominal tooth root stress. So that's a maximum local principal stress. Okay, I hope you can hear me. The nominal tooth root stress, and you'll do that for a perfect gear made perfectly without any errors. So as a designer, you will say, that's my design of gear. I'm going to work out the nominal stress of something that's made perfectly, installed perfectly and looked after. But then this is where the engineer comes in, not the mathematician. You will say, but I know life isn't perfect. I'm going to take that nominal stress and I'm going to decide how well it's going to be made. I'm going to decide how well it's going to be inspected. And then I'm going to find out what sort of load variations are going to come in practice. Remember what we saw on the wind turbine. So yes, I'll do the maths and work out the nominal stress, but then I'll have to get off my desk, go around the shop floor. How accurate can I make it? How good are those machines are going to make it? And make a decision on the accuracy. And then I will change those stresses, saying it isn't perfect. I'm going to take account of manufacturing and then installation and load variations. And that's the message to get across. You will do that. And the standards will demand you do that. And the allowable bending stress, again, we work at endurance limits. And the truth is, it's fatigue. Very quickly with gears and gearboxes, you get up to infinite life. You soon get 1 million cycles of load. So you need to start doing testing of the materials, finding out all about it. And again, one of the many standards goes through in much detail how you sort out the material. So everything you learned about material properties, yes, you're going to have to know that. Surface damage you have to avoid. I mentioned what happens with gears and gear teeth. They not only roll together, they slide. And we put massive amounts of forces there, and we need to make sure the surfaces are well lubricated. And yes, there's more standards about. And yes, they will help you. And you don't just read these in an afternoon. It will take you quite a long time to go through those, understand them, but you must use them. And you're very lucky today because there's lots of software about which have programmed all these things. But even if you use a program, you need to spend some time understanding it. So you're using the program properly. To avoid surface damage, you have to separate the surfaces. And so you have to start thinking about how we're going to manage that. And all gear teeth transmitting any significant amount of load, we develop a hydrodynamic oil film between them. We have to develop an oil film. And it's great. This is why we use lubricants, because oil is wonderful, because it gets stiffer under load. So we work out what the oil film is in there. And we also use elastrohydrodynamic. And when we call it that, it's because we take into account how much the gear teeth deflect to calculate the oil films. And then, depending how much load you're transmitting, what the temperatures in the mesh are, it will decide what your oil film is. And then you will have to make a decision. Will a straight mineral oil work? Or do I need to put something with anti-wear additives in there? Or do I have to put some extreme pressure additives in there? And again, the standards and the experts will help you to do that. And the oil companies are invaluable in the help they do that. Thermal issues. And again, gears aren't 100% efficient. You have to start looking in there, depending on what oil films you've got in there. Is it mixed film? Is it hydrodynamic, elastrohydrodynamic? The coefficient of friction changes. Calculate the power loss. And then you've got to get rid of the heat. And then you've got to make sure that gearbox can get rid of the heat, because if it gets too hot, the oil gets too thin, you don't protect the gears, and you've got to get rid of that heat. Even if they're 99% efficient, you still have a lot of heat to get rid of those gearboxes, and you have to design and make sure you do that properly. I'm sorry if I haven't finished. I know some people are leaving, but I will carry on to the end. And as Kirsty said, there will be a recording of this. If you want to see things you've had to miss, get that to Kirsty and we can understand and let people look at the recording. I am going to be a few more minutes. I apologise if you have to go. And I know a lot of you are supposed to be on holiday today. But looking inside the gearbox, nothing is rigid inside a gearbox. Remember those bending moment diagrams, those shear force diagrams, looking at bending moments. Yes, we need to work those. You will need to work out across the face of those gear teeth, how much is it bending? What are those shaft deflections? Because that will change the gear rating. So all of those bending moment diagrams, shear force diagrams, yes, those are critically important when you're designing gears and gearboxes. The material specification, again, in order to cope with those loads, I put too much on this slide and no, you can't read it, but I will tell you this now. If you want to prove your gears to ISO 6336, you will need to get material which is properly specified. And for that material, there's 14 different places where you will have to get certification or prove the material as good as the spec says. And that includes cleanliness, hardenability, grain size, all of those things are in there. And people have put years and years of effort into creating these standards. And the great news is there's lots of incredibly reputable manufacturing steel or material suppliers who can do this for you. But if you want to get gears to fit the standard, you must ensure you get your gears from a reliable source. And before you start making anything with them, make sure you've got the certification necessary. Hardness, we will heat treat gears, and those are typically that diagram there. If you look at this diagram there, it's typically what we look for. To transmit large amounts of power, I need a case hardness on there. That diagram there showing Vickers hardener, and so that's a measure of the hardness. The x-axis going up is hardness, and going in, it's a depth. And if we nitride gears, we can get very high hardnesses, but only get quite a shallow case depth. If we carburize and case harden them, we can get pretty hard surfaces, but much thicker case depths. And if we induction harden them, we can go to really thick case depths, but not so hard. But all of those things allow us to do it. And so again, pretty much every gear manufacturer will rely almost entirely on the quality of their heat treatment, or the people who do their heat treatment, because the case hardness you get is critical in determining whether those gears are going to do exactly what you expected. Material science, this is metallurgy. Yes, you do need to listen in your metallurgy lectures. I know when I was at college, I have to be honest, metallurgy was the most boring thing we ever did. We spent our time looking down microscopes at martensite, sketching pictures of pearlite. But then I went into industry, went to a heat treatment facility, and it was like magic. You could actually see people heating and quenching steel, and you fully understood, appreciated the criticality of the heat treatment process. And it's quite staggering. I do mean it. If you ever have the chance, keep safe, but go and see how people heat treat it. It's incredibly, it's more than blacksmithing. It's then you will appreciate metallurgy and how important it is. Another unavoidable truth, that gears, unless properly managed, gears and gearboxes will be incredibly noisy. You've got to manage that. And in some applications, you don't want to make your workforce deaf. You don't want to do those things. If it's a defense application, you have to make silent gearboxes so the enemy can't hear you. So you have to manage that. And managing noise and vibration is a very specialist subject. Yes, you have to understand the system response. Because with gears and gearboxes, we always get a torque reaction. The forces have to go to Earth. So on their route to Earth, the gearboxes can, just like a loudspeaker, sorry, I should go back to that diagram. There's a picture of a loudspeaker there. See that gearbox there driving a conveyor? As the torque reaction forces go to Earth, those forces will be vibratory. You cannot avoid that. Each of the forces going to Earth from a gearbox will have a vibratory content. And if on its journey to Earth, it comes across parts of the structure that act like a loudspeaker, it will produce noise just like a loudspeaker does, or even I am now, the diaphragm with my voice. And so you need to make sure, first of all, you're not making much vibratory force anyway, but also on the way to Earth, there's nothing that's going to act like a loudspeaker. And that's what this next diagram is showing us. We look at the system stiffness and the mobility of the stiffness. Now, stiffness, you understand, it's how far things deflect when you put a force on there, but mobility is something different. It's how much does it vibrate when you put that force at different frequencies. And so that gearbox there, it's courtesy of David Brown, but they've designed that gearbox there, that gearbox has pretty much zero mobility at tooth contact frequency. So the frequency where the gearbox may produce noise They've designed that gear case to have zero mobility. It just doesn't respond at those frequencies. They've tuned the gear case to make it quiet. And that's a whole specialist subject. And again, within the system, you may get torsional vibration, and so you've got to make sure you get no resonance. If it's a high-speed gearbox on journal bearings, you may get transverse vibration, so you've got to spend time avoiding transverse vibration or torsional resonances. Again, the whole system you have to understand and learn. Transmission error, I'll raise this. If you ever get involved in noise, this will become like the holy grail. You've got to reduce transmission error, and transmission error is, look at that diagram there at the top. I'm modeling the gear teeth such that there's one tooth stiffness connecting those two lump masses. And as the gears rotate and transmit force, anytime that tooth stiffness deflects, and it will, that's giving you transmission error. It means you're not getting a constant velocity ratio. Tooth stiffness changes, vibratory forces come there, and you do whatever you can to reduce that transmission error. And the diagram at the bottom left is somebody predicting transmission error. And the scale on the left there is tenths of microns. Okay, so we're looking at 0.1, 0.2, 0.3 of a micron. You're working at those levels, if you like, to produce pretty quiet and silent gears. Again, a whole specialist subject. Even better news is that some of the software you can buy to rate gears will help calculate transmission error for you. And you need to understand that to start playing with tooth design, whatever, to make those gears as silent as you can. And quickly then, I will talk then about not only to make them silent, you have to make them incredibly accurate. And I will make this statement now that gear teeth are amongst the most elegant, precise and accurate mechanical components. Those are pictures of people measuring gears, and gear metrology. When I say it's accurate, I truly mean that. This is part of the ISO standards on tooth quality. The red one there is a grade 7 gear. And for a lot of people, that's probably the lowest quality gear they'll get away with. But I have to emphasize a point. When I look at that red shaded area on those two standards there, where we're looking at pitch errors, cumulative pitch, radial run height, profile, all those things there, those numbers of microns, 713, 1114, do you know what those are? Those are the same size as white blood cells. So typically, the most inaccurate gears, most people are making these gears, are demanding tolerances which are no bigger than white blood cells. And people outside the industry do not believe that we have to make gears that accurate. You go towards the left to those pretty silent grade 1, 2, 3 and 4, it's almost unbelievable level of qualities you have to get. So gear measurement is again something else which is a very specialist subject. And I'll try not to keep advertising the British Gear Association, but we have a special interest group on gear metrology. And if you're members there, you can join it and you can help to calibrate your measuring machines. We have artifacts we send out so everybody can measure their gear and they can do and check how accurate their machines, all the metrologists their users are. I'll quickly finish up. We're getting close towards the end. I apologise for going a bit over the hour. But equally, I've gone through all the design things there and I measured accuracy of manufacturing, but there's so many manufacturing options. You can make gears by forming, by casting and moulding, or by machining. And this is the area which is changing perhaps more than anything. It's quite staggering, the new technology we have about, and we need to get up to speed with these things. So machining, that's a nice rack. This is what involute gears are so, became so important, because you can make very accurate involute gears with very simple rack-shaped tools. And we've used this for over 100, nearly 200 years. We've used racks, hobs and whatever, producing incredibly accurate gears. But now the world is changing. we've moved on from mechanical machines. We have digital machining options. And so we have 5-axis, 6-axis machines producing new and novel ways incredibly quickly and accurate. And again, within the British Gear Association, we have a special interest group on, we called it 5-axis machining, but now we call it digital machining because there's so many things going on. And there's a group of people sharing knowledge on these new methods and doing tests and getting data on these new manufacturing methods. Forming options, sintered gears, and again, sintered gears, there's incredible developments going on with sintered gears. And with sintered gears, you just take powders, you compress them, you make a very expensive dye, you compress the powders, you make a green one, then you heat it to very high temperatures and produce a sintered gears with no debris in there. And people are taking the opportunity to put damping materials in there and to put different constructions there to make gears silent, to make them quieter. And CNC technology is making that get better and better. Additive manufacturing, that's something else. Everybody talks about 3D printing. And so that picture there on the left, that's the first additive manufactured gears that we had made by the BGA almost 20 years ago now. And that's changing significantly. Even as we speak, some collaborative research is going to be done by the BGA where we're going to make some additive manufactured gears, laser printed or digital printed gears. And we're going to test how strong they are. We're going to see just how strong these 3D printed gears are and do some testing just to understand, because the technology's changed so much the last few years. And so we'll have some collaborative research going on to do that. So now I'm nearly at the end. We started 4,000 years ago with self-pointing chariots. And now I want to talk about Industry 4. Just the last few slides to really excite you to say, look, all those things are going on, lots of opportunities, but it's getting even more exciting now. Smart connected products, the Internet of Things. This is an example that David Brown sent us all of. Let me show you. It's where we've got the smart connected products. And so we've got this gear watch. You actually put a plug in the gearbox, and this actually measures noise, vibration, lubricant content. And instead of somebody going around inspecting, taking measurements, this goes through a very safe grid, back through the internet. And so a specialist engineer will keep an eye on this and report back to you what's going on with it. And so that's smart connected products, the Internet of Things. That's been going a few years now, and that's incredibly useful. So you've got a big brother watching things to make sure things are going incredibly well. And it helps you. You can get experts in to help you, and that's 24/7 monitoring of things to know things are going amiss or going well. Then there's digital twins, and this is quite staggering. This is what we call digital twins. And what I've got on the left there is a picture of from some of the gear rating software. We've got there is the picture there of what the theoretical tooth flanks. So we said we're going to make this gear, we're going to make it to say grade 4, 5 or 6, and that's what we're expecting. On the left, the top two pictures are showing the measured tooth flanks. And then we go over to the right. Well, for that theoretical tooth flanks, that's my stress distribution. That's what I'm expecting, the contact stresses, how they look there. And then I can decide, is that going to last long enough or not? But now with a digital twin, this is worked at the design unit at Newcastle University using Untitled software. We're measuring the tooth flanks, and we go across there and say, actually, that isn't what we expected. And it's taken, well, I'm going to take those actual measurements, re-look at the contact stress distribution and say, by the way, this is what your new stresses look like. Are you okay with that? Because you may have to reduce the life of the components or what have you. Or you may say and feed it back to the system, well, actually, no, I'm not happy with that. And this will tell you exactly where to put things right and change it. So we can do this, and now even as we speak, people are linking this to the machine and the grinding machine, taking these measurements, and this digital twin is saying, no, that's not good enough. No human interference. They're going to change it and say regrind it to get this. That's again another BGA member is developing this industry for. Next thing, autonomous measurement. Hexagon, one of the leading people in gear measurement. First, we've got autonomous measurement. On the left there, we've got something where I often say that if you've got a very accurate measure machine, you better make sure you've got a trained metrologist to drive it. What Hexagon developed is robotic measurement. And so if you're mass producing, yes, I know that thing there, this robot will take that component, put on the measuring machine, do all the measurements. So 24/7, if you haven't got in that shift system, you can have this robot, this autonomous you don't have to have your metrologist there 24/7. Yes, he can help program it and do those things there. That's going on there. 24/7 asset management, making sure your key machines are running at the right speeds and feeds and everything like that. Those things are going on. And what we have at the BGA is Technical Awareness Day. So all these people we're talking about here with these technologies, yes, they do make presentations so members can understand the latest developments. One final thing, which is perhaps the most scary here, this is transmission dynamics, have developed machine learning. So what we've got here on rail tracks, in railway engines, we've got smart oil plugs put in there. Now, we talked about the gear watch system where you're monitoring all the time and somebody's looking at it. This goes a step further. This is machine learning. Not only is that oil plug picking up the data, looking at it, but it's learning. It's taking that data and saying, oh, I've seen that before. It's doing this. And the machine is like Big Brother doing all of these things. And it looks like this. I don't know if you can see that diagram, but that gear, that smart oil plug is decided, I've seen that before, out of all these 40 different gearboxes, that means that gear's got insufficient gear tooth tip relief, it's got high vibrations, some ghost frequencies, all these things are going on. So I'm going to finish now. I've kept you too long as it is, but any questions? I'm going to put up the chat thing, see if there's any questions. Kirsty can come in and tell me if there are any. But we've gone from south pointing chariots to Industry 4 about everything that's great. And the only message I've got across is yes, while we have machines, we're going to need mechanical power transmission and gears. We're always going to need gear engineers, and life is becoming more exciting. And if you think the challenges for the last 200 years are bad enough, we're going to cope with global warming and all the things we have to do to put this planet right. Engineers are going to have to get involved, and there's lots more wonderful challenges which we'll have to embrace and help. So I'm going to be quiet now. I'm going to open up the chat to see if there's any questions there, and if not, please put them in there and we can pick up all the questions, and if you would like to, and send the questions to Kirsty and myself, and we'll get back to you. Any questions about anything we've shown there, get back to us and we'll answer them to you.